So in this second video on solving systems of DEs involved, we're going to see what we have to do when the eigenvalues are complex. So you recall that in the last video, the structure of our solutions was C1 e to the R1 t U1 being the first eigenvector associated with R1, plus C e to the R2t U2 U2 being the eigenvector associated with the eigenvalue R2. Whereas, so that was the case when we had when we have real eigenvalues. But when we have complex eigenvalues, the structure of the solution is different. Just like when we had complex complex solutions to our characteristic equation before, we had a different structure to the solution. So the solutions, we call them separately x and y. They look like this. So here are what what the solutions look like in the case when we have complex eigenvalues, and actually we have complex eigenvectors too. Remember that when we solve something involving complex numbers, we get an an alpha plus or minus beta I. So alpha plus or minus beta I are the eigenvalues. And and you can see that the alpha and the beta show up in the places where they did before as the coefficient of the exponential and the coefficient of the cosine. So that structure looks familiar. What's different is that we also have this vector A appearing here and here, and the vector B appearing here and here, and those vectors A and B come from the they're not quite the eigen vectors of the in this case, but they come from the eigenvectors in this case. So let's take a system that looks like this type, or that will have complex eigenvalues and eigenvectors, and see how to solve it. See how to find the alpha, the beta, and then the A and the B. So here's our x prime equals ax. Here's our matrix A. We find the determinant of A minus Ri. So that's minus 1 minus R. We don't change this entry or this entry, but we change those on the so-called main diagonal. That's this diagonal, top left to bottom right, and subtract R from them and form that determinant. So remember, this direction is positive, so it's, instead of writing minus 1 minus R, let's write the negative of 1 plus R. Instead of writing minus 3 minus R, let's write 3 plus R with another negative. And then remember, this direction is negative, so we are subtracting 4. So what's here is what? R squared, it's positive because it's negative, R squared plus 4R plus 3. So let's fix that. This entry here should be a minus 1, and this direction is the positive direction, and find the determinant. So instead of writing minus 1 minus R, let's write it as 1 plus R with a negative taken out. Instead of writing this minus 3 minus R, it's 3 plus R with a negative taken out, and then this direction is negative, so it's the negative of negative 2 plus 2 equals 0. So all of this is positive. R squared plus 3R plus 4R plus 3, and then plus 2, so it's R squared plus 4R plus 5 equals 0, and that quadratic equation has solutions negative 4 plus or minus the square root of b squared minus 4ac is 16 minus 20 over 2, so that's negative 2 plus or minus, or negative 4 plus or minus 4I over 2, so it's negative 2 plus or minus 2I are the solutions to this, to the determinant, and that tells us that alpha is minus 2. Let me write it over here. Alpha is minus 2, and beta is just the coefficient of I. It is 2. And so we already know that the structure of our solution will look like this: e to the minus 2t cosine beta 2t minus, well, actually there's a vector a here, remember, that we have to find, minus e to the minus 2t cosine beta t, and then there's that vector b that we have to find. That's our x of t, and our y of t is similar, it's just that the sine and cosine are in different position. E to the minus 2t sine 2t, vector a to be found, e to the minus 2t cosine 2t times the vector b. So how do we find those vectors a and b? We set it up just like before, but remember that our eigen values in this case are 2 plus or minus 2I. When we plug those in, all we have to do is pick one. So let's set our R equal to 2 plus 2I. We don't have to do it twice in this case. And so we subtract 2 plus 2I from the main diagonal, and then use that to find U1 and U2, and we actually find both we find both A and B in one step in this case. So this entry is a minus 1. We're subtracting 2 plus 2I here, and this entry is a 2. This entry is a minus 1, and this entry is a minus 3, and we're subtracting 2 plus 2I here. So let's resolve that matrix, and so if we subtract 2 plus 2I in this position, we're going to get what? Sorry, the eigenvectors were minus 2 plus or minus 2I. So this is a minus 2 here and a minus 2 here. So minus 1 minus the eigenvector minus 2 plus 2I gives us 1 minus 2I here. This one stays the same as a 2. This one stays the same as a minus 1. And then minus 3 minus 2 plus 2I becomes a minus 1 minus I here. So we're solving that times U1, U2 equals 0, 0. So let's pick that up on the next blackboard. So as before, we get two equations. Remember, in the case when we had real eigenvalues, the two equations were just multiples of each other. They're not multiples of each other here. They give slightly different structures, but we only need to find one of them to find those unknown vectors A and B. So let's just take the first equation, which is this, and then let's take the second equation, because if we take the second equation, we won't have to divide by 2, so we won't have any fractions. So we get minus 1 times U1 minus U1 and then that times u2, so it's plus, but there's a minus we can factor out. 1 plus I u2 equals 0. That's the same as minus u1 equals 1 plus I u2, or u1 equals minus 1 plus I times u2. And remember what we're doing when we set up one of these, or when we find the eigenvector, is we just need the relationship between the u1 and the u2. So if u1 is minus 1 plus I times u2, let's put the u2 out here. Since we've done this a couple times, we're going to factor out. And here, let's do it first this way. And the u2 is here, and then this is just u2. But if we factor out the u2, then this entry goes to a 1. And so this right here is our relationship between the positions, which, as you can see, is a little bit more complex than before. And what we're going to do is write that in an a plus bi form. And so isn't it correct that if we write this a plus bi form, and we put minus 1 here and 1 here, and minus 1 here and 0 here, and we look at this, adding up the entries. So if we add up, we get, in the first entry, we get minus 1 plus minus 1 times I. So we get minus 1 minus I in this top position, and if we go to the bottom position, we get 1 plus 0I, or just 1, and that matrix is the same as this matrix and this matrix. And so what we've done actually is we've gotten the A and the B. The A is the part that doesn't have the I in it, this vector minus 1, 1, or the vector that's not multiplied by I, and the B is the vector that is multiplied by I minus 1, 0. Notice that if we'd solved this other equation, that times that, we would have gotten a different A and B, but it would have been a valid solution that is essentially a multiple of the other solutions. If we go back to the structure of our solution, which we had right here, we can now fill in the vector A as 1 minus 1, or as minus 1, 1 appearing here and here, and the vector B was what, 1, and the vector B is 1, 0, which appears here and here. And so we now have the solution of this differential equation, which has eigenvalues minus 2 plus or minus 2I, and eigenvectors we just saw were what? Here's the A eigenvalue appearing here and here, or the A part of the eigenvector, appearing here and here, and the B part of the eigenvector appearing here and here. So this concludes this video on solving a system of DEs where there are complex eigenvalues and eigenvectors.